Okay, we're in 13.2 now, and we're going to look at the two-sample t-test. So we're going to, again, like we talked about in 13.1, we're going to look at the difference between two means. And so we're going to start by hypothesizing, because again, like for the credit card example, we're going to do samples. So we're going to send an incentive to one group, and then maybe a different incentive or no incentive to a second group to try to get information about the population, because again, the population's big. It might be 1,000,000 people. We can't talk to all of them, so instead we'll talk to a group of maybe 100 in group A, 100 in group B, something like that. Well, we're trying to estimate the difference between what will happen if we apply our incentive across the entire population. So we're going to look at a difference in spending habits between the two samples, and then we're going to use that to hypothesize what will happen for the bigger group, the whole population. So we're going to start with a hypothesized difference, and we introduced this Greek letter delta in the previous section. We're going to call this delta 0 or delta naught, and it's that's going to represent the difference in the population means. So if we rolled this incentive out to the entire population, or if we didn't roll it out to the population, what would be the difference in, say, our spending habits? So what we're going to commonly do is we're going to say it's going to be 0. And what that means is we're going to hypothesize that the spending habits of the full population, all 1,000,000 people, will not change based on the incentive. That's really what this means, is that their average spending with the incentive or without the incentive would be the same number. So if you subtract them, you get 0. And that's what this says right here, delta naught equals 0. Okay, so here's the math we're going to do. We're going to say our null hypothesis is the mean spending of our group 1 minus our mean spending of our group 2 is equal to delta naught, which we're going to assume is 0. So we're going to say the spending habits of the people who get the incentive versus the spending habits of the people if they didn't get the incentive will be no different. So we're going to assume our incentive doesn't create a different spending pattern in our population, and then we'll see if that's held up. So we're going to have to calculate a t-score. We'll do that by taking the sample spending mean minus the sample spending mean of the two different groups, subtract our delta naught, which will be 0, and then we'll divide by the standard error of y bar minus y bar 2, and we have that calculation down here. So we're going to compare the standard deviations of both samples. So the standard deviation of spending for group 1, the sample standard deviation for group 2, and we're going to compare that to the group sizes, so those could be different. And let's actually look at an example to really help us get this. So here we have a website design. So it says a market analyst wants to know if a new website is showing increased page views per visit. A customer is randomly sent to one of two different websites offering the same products but with different designs. Given statistics below, run a hypothesis test to determine if there is a difference in the mean number of pages between the two websites. So the idea here is we send these customers to one of two websites. Each website has a page, let's say per item, and we want to see how many pages they go to. So obviously the more pages they go to, probably the better our website, because that's indicating that we're keeping them longer, we're making them hopefully contemplate buying the products, maybe more than one product. So here's our two groups, website 1, website 2. Notice our ends can be different, that's okay. So we have 80 people went to website 1, 95 went to website 2. The average number, or the mean number of pages viewed from website 1 was 7.7 pages. The mean number of pages viewed from group 2 is 7.3. Notice that's slightly different. The standard deviation of pages from website 1 was 4.6. The standard deviation of pages from website 2 is 4.3. So now notice you should be glad if you get the information like this, because it's got a nice table. All your symbols are matched to a number, so it really becomes a plug and chug. You don't really have to spend a lot of time deciphering from text or from a paragraph what numbers go with what letters. So it does become a plug and chug. We have all that previous information. We have all the information for the equations we have on the previous slide. It looks like a lot here, but let me break it down. So again, our null hypothesis is the number of web pages, the mean number of web pages based off of website 1 is exactly the same as the mean number of pages seen from website 2. Our alternative hypothesis is two-sided. Notice, this just says that they're not the same. So maybe one has more, maybe one has less, but we're not sure. So we just say our null is they're equal, our alternative is that they're not equal. So we're going to find a t-score. So we're going to take the mean number of pages viewed based on website 1, subtract the mean number of pages viewed from website 2, divided by the standard error of y bar minus y bar 2. And if you just match the numbers from the previous slide to here, you will see, so if you write down these numbers and these letters, you will see that they match to what we have here, and our t-statistic becomes 0.588. So now we have to use our chart. Oh, and I should say, so to use a t-chart, we need two things. We need the degrees of freedom, and we need our t value. So we're going to have our degrees of freedom is 163-ish. Now the way we got that is from this equation. I don't have the numbers substituted in, but it's basically the same thing. You know S1, you know S2, you know N1, you know N2. That's all you need. So you're going to plug those numbers in. Whenever you see an S1, you use 4.6. Whenever you see an S2, you use 4.3. Whenever you see an N1, you use 80. Whenever you see an N2, you use 95. So if you plugged in those numbers across this equation, crunched it out, you would get 163. So now we have to find the p-value for a t-score being greater than 0.588. And if you look up either in the t-table or you can do this with technology, there's a way to do it in Microsoft Excel and your calculators. I think many of your calculators will have a t-test is what it's called, and you can plug in the various values here and it will just spit out that the p-value for t being greater than 0.588 is about 0.5573. And so p-values, again, we decide what's low. So we pick an alpha level, and so we pick an alpha level of typical numbers are 0.05, 0.01, and so we're going to say if the p-value is less than that, 0.01, 0.05, we will reject the null. But this is actually a pretty large p-value, 0.5. So that's much larger than 0.05 or 0.01. In fact, that's 10 times larger than 0.05. It's 50 times larger than 0.01. So we would definitely fail to reject the null hypothesis. So what does that mean? Well, it means there's no evidence based on the two samples that the mean number of web pages visited differs between web page 1 and web page 2, which in layman's terms just means it doesn't really matter which website they go to. So maybe our new fancy website we made, website 2, isn't really changing consumer habits. Okay, now if we do a 95% confidence interval for this, that the true difference in the mean page visits between the two websites. So now we've got the difference in the means. So again, a confidence interval, we're going to have our mean value, but in this case, again, it's a difference in mean values, plus or minus our margin of error, and in this case, our margin of error is a critical t-score, times our standard error of the difference in our y bars, which is just this equation we saw before, with that degree of freedom again. So based on this degree of freedom and this confidence level, you can look up this t-star from the t-table. It's 1.9676, and we already calculated this before. So this says we're 95% confident that the true difference in mean. So basically what this means is we're 95% confident that if you subtract these two values here, you're either going to get a value of negative 9.38, or if you subtract these two values here, you're going to get a value of 1.7, and any value in between. So we think the true value of the difference in these two means is between minus 0.9 and 1.7. Now the key to that is if 0 is in this interval, so if it goes from negative to positive, there is a very likely chance that 0 is in between these two values. That indicates that backs up our p-value calculation that that there is no difference. And in fact, this is the method we're going to use in class, because finding a p-value of a two-group t-test is kind of beyond the scope of this class. I may give you problems in the future where I give you a table and I give you the p-value and then you have to interpret it. So small, reject the null; large, fail to reject the null. That's what you have to know there. But we're mostly going to do this method. So we're going to do a confidence interval, and all we're going to look for is 0. Is 0 in between these numbers? In this case it is, and so if it is, we're going to fail to reject the null, because there's a very good chance that 0 is the answer based on that, and a 0 means there's no difference between the two means. Y bar 1 and Y bar 2 are probably really close and possibly the same number, so if I subtract them I get 0. And so we should get the same conclusion here as when we ran the p-value test, and this will be the method preferred. And that's going to do it for 13.2.